welcome to the CTS Innovation Hub webinar. So we are happy to see so many people who have registered, and we are ready to start now. So I will be your host today, and I also have another speaker, Baltramiejus Andrijaitis from from CTS in the Czech Republic. So he'll be talking after me.
Hello, everyone.
Hello.
Thank you for joining.
And so Baltramiejus, you can hear me, and I'm going.
Yes, I can hear you, and I can see the screen.
Good. Thank you. So we will start now. So first, let me just get a laser pointer. Okay. So the program of my first part of the talk looks like this. I'll give a very short introduction to CTS and to the Innovation Hub. Then I'll be talking about the RoHS legislation, which is, in our view, basically about banning lead in PCT. This is a very short version from our perspective. I'll be talking about the revision of the RoHS-directive, and then I'll end by giving some overview of some alternatives of PCT that are lead-free. Okay. CTS is a American-based company, but with a presence both in the United States and in Europe, and also in Asia. So I'm from the site in Denmark, and as I mentioned, Baltramiejus is from the site in the Czech Republic. So there are two divisions. One is sensors and mechatronics, where most of the products go to the automotive industry. For example, foot controls like pedals for cars. And then in the advanced materials and solutions divisions, we find the piezo products, where we are working. So let me just tell a little about the piezo products. So there are quite a few different types of piezoelectric products in our line. We have the well-known bulk ceramics. We also in one of our American sites, we make single crystals with very high performance, up to 100 millimeter of diameter. We also make piezo devices in the CTS with custom assemblies. We have quite a big production of multi-layer components, especially for actuators. Here in Denmark, we make also thick films that are very well suited for specialized high-frequency ultrasound applications. And also CTS has a manufacture of transducers, and for example, some transducers that Baltramiejus will talk about later. Okay, and about the Innovation Hub. So this is an initiative that we started, where the idea is to interact with partners and with people in the field in another way than simply selling parts to customers. So it goes all the way from the idea stage and with different modes of collaboration right until entering the market with some new product that may have been initiated somewhere outside our company. But the webinars are located here in the idea stage. So let me go on and talk about the program for today. So this is webinar number 2. Well, the second part of the talk will be approximately 3:30, and it will be about some specific application of some lead-free ceramics. But I will start now with an overview of legislation and the status of how it is looking now, and also give some overview of some lead-free materials. So first, a little bit about the background of RoHS. The first RoHS-directive came in 2002 and was updated in 2008. As you may know, RoHS is an acronym of part of the title of the directive, the restriction of the use of certain hazardous substances in electric and electronic equipment. And maybe you think it's only about lead, but it's actually about a lot of different hazardous substances. Some are organic, some are inorganic. But some important substances in target are the heavy metals, so mercury and cadmium, and of course lead. So luckily, there was an exemption for PCT, as I'll show you in a minute. And this is also the case for the newer version of the RoHS directive, which we call RoHS-2, that came in 2011. So this is a part of the Annex 3 to the RoHS-2 directive, where you see how it looks. Exemption number 7C1 looks like this, and there is a specific mention of so-called piezoelectronic devices. That means that we could continue to produce and sell PCT on the European market, even though lead is, of course, targeted, as I said. So I should maybe just give a few details about what how the directive is constructed. So basically, it's aimed at so-called EEE, so only equipment which can be called electric and electronic equipment. And you see part of the definition here. So one important point is that there's voltage limits. So the EEE is only voltages below 1000 or 1500 volts for AC and DC voltage respectively. And it could either be a component or an assembly that's used in a finished product. There's a lot of exceptions for the scope of the RoHS-2 and the original RoHS. So, for example, military products and products that are targeted for sending into space are not in scope of the RoHS-2. And there are a number of different exceptions that I'll not mention specifically, but you see a list here. And part of the directive is a little bit difficult to read for people who are not familiar with this kind of literature. So there's, for example, so-called non-road mobile machinery for professional use. And if you don't know what that is, you can just read the definition here, which maybe also requires a little more scrutiny before you actually know what they mean. I'm not, I cannot explain exactly what is meant by this, but if you are in doubt, please find help from experts in the field. Okay, I will go on with the more recent development within RoHS. So the important thing about these exemptions is that they are not for forever. They are intended to be updated, and the idea is to take into account scientific and technical progress, as it says. And this is with an update interval of 5 or 7 years in our case, depending on the application category. And because of these updates and let's say time-limited exemptions, a European cross-industry project was started in 2013, and we were participating almost right from the start, and also collaborating with the Japanese electronics industry in order to give a common input to the process. So we sent in an exemption request back in 2015 asking for an extension until 2021. And I'll try to make the story a little short. In the end, we waited until 2016, and finally a report came with a recommendation of a shorter time limit of only 3 years. But then, thanks to an intensive effort from the industry to really convince the EC officers, we managed to modify this a bit, so this suggestion was not adopted fully. In reality, in 2018, a new version of the directive came, which was basically just an amendment to the list of exemptions. And you can see here how it looked in 2011. You know, I showed this before, but then in the new update, there's actually expiry dates that are put into the directive. And the earliest dates were in July 2021, and in some cases it was 2 or 3 years later for specific categories. And you can simply look up the RoHS-directive if you want a definition of these 11 categories. I'll not go into details on that. But still, the deadline for filing a request for renewal is 18 months before the expiration date. Now it's quite important just to make the point that as soon as you have made a valid exemption request, at least 18 months before the expiry date, then as long as this is under evaluation by the Commission, the exemptions are still valid. So they are valid until a decision about this renewal request has been made by the Commission. This is a very important point. And it may actually take, for example, 2 years for the Commission to take a decision on such an exemption application. So based on this, we made in our company a projected timeline back in 2021, and it looked like this. This was the original deadline for most categories in July 2021, and the request was submitted in 2019, December, and then expected evaluation time of 2 years. Then this report, the evaluation report, was made by this independent consultant working for the Commission, and it was planned for September 2021. And then basically, in the worst case, if this evaluation by the Commission resulted in a no, there will still be some 4 months until this draft delegated directive came out, and then such a directive would give a transition period of 12 to 18 months, and then that would result in let's say a worst case scenario of the exemption expiring in mid 2023. So of course, if you have seen this before, you may have wondered why nothing happened in 2023, which is almost past. But the explanation is actually that there's been quite some delay. We've checked on the situation, and I can give you some new information now, even if you saw part of this before. So the status as of October this year is that basically there was with some delay that this report came from this Öko Institute, the consultant company, and in this report there was a recommendation to split the original exemption that we were looking at into 2 different number 5 and number 6. Number 5 not so important for us. It's about glass or glass matrix, and then 7C6 was supposed to be piezoceramics, and then ceramics with a positive temperature coefficient, which is not very precisely written. So I added of resistance because the directive is a little bit vague here. But so actually 2 rather different types of ceramics are put into one here, and one problem with this wording is that there are other lead-containing piezoelectric ceramics than PCT. There are some that do not contain zirconium, for example, and so this wording was not so good, and also there were quite a few pyroelectric ceramics containing lead that seem to fall outside this exemption. So from the umbrella project, this cross-industry project, we have sent an objection, and our recommendation is to keep the wording that you saw already in 7C1, and then also to keep the deadline as suggested by the Öko Institute for July 2026. And the latest news from October is that this draft delegated directive is expected in Q1 next year, in 2024. So when this comes out next year, there'll be specific dates that we can count on. But we hope that they will actually accept this deadline of 2026. So now I can give an updated timeline. So again, you see the original exemption expiry here, and this is the request for extension I mentioned already. Then actually the actual publication was in December, as I mentioned, of this report, and the suggested expiry date, as I told you, was July 2026. The evaluation actually ended up taking much more than 2 years, basically closer to 4 years, because they have been quite overloaded with work in this office in the European Commission. Anyway, from this, if we take a worst case, and we could get a rejection of the exemption request, then there will still be around 4 months for this new draft delegated directive, and then a transition period of at least 12 months. So you could say that this is the worst case or earliest exemption expiry, but from what we have heard from people very close to the process, it's more realistic to go to a let's say plan for this date here, July 2026, which also means that in this umbrella project, we will start work now on submitting a new request for extension in January 2025, which will again be 18 months before that expiry date of July 2026. So this is as much as I can tell you now about the status of the RoHS-2 directive. Okay. Now I have time to go a little more into technical details, which I hope some of you will appreciate. So first, before going into the let's say description of lead-free alternatives, I'll just remind you of some concepts from piezoceramics, which is really known from PCT. That what we call soft PCT is donor doped. It's doped with certain dopants that we call donors, and we also have something called hard PCT, which is acceptor doped. And the reason for these categories is that there'll be very specific characteristic properties of these two types, as I'll show you here. So if you take functional properties such as dielectric properties, permittivity and dielectric loss, and some mechanical properties like stiffness and mechanical quality factor, and finally ferroelectric and piezoelectric properties like the coercive field and the piezoelectric coefficients and the piezoelectric coupling, you can see very specific tendencies for the hard and soft PCT. So beginning with the soft PCT, generally you'll see an increase in permittivity and also in dielectric loss. Both stiffness and QM will go down, as well the coercive field. It becomes easier to dipole a soft PCT than a PCT which is not soft dope. And finally, you'll get generally higher coefficients and coupling. And what about hard? Well, it's very simple. All the arrows point in the opposite direction. So all the tendencies are in the opposite direction. And for example, normally you would appreciate to have a lower dielectric loss, which you get with a hard PCT. So when I stress that it's a donor and acceptor doped PCT, the point is that you cannot really say that in order to get it for the lead-free ceramics, you need to use a donor type dopant or an acceptor type dopant. It's not generally as simple as that. Sometimes you need to use other strategies than simple donor and acceptor doping. Okay, so now I have a long list of alternatives to PCT, lead-free alternatives. So starting with the best known and the one that has been known even longer than PCT, which is barium titanate. And then I'll actually use this this category of soft and hard, but I put it in citation marks because the categories are not quite as in PCT, but still it makes sense for some users of piezoceramics to think of soft and hard categories. And I also put high T, meaning can it be used at high temperatures. So first, barium titanate. Well, it's possible to dope barium titanate both to obtain soft and hard properties, different dopants, of course. But it will never be well suited for high temperature because the Curie point is close to 120 degrees C. Then let's say a variant of the barium titanate, which is modified with calcium and zirconium. Well, you can get even softer than barium titanate. You'll generally find it difficult to get hard properties, and certainly it's not useful for high temperature because the Curie point is even below 100 degrees C. Next, very well-known material, KNN, potassium sodium niobate. And just for those who haven't seen it before, when I write K, Na, it actually means that like up here, the sum of the coefficients on potassium and sodium here will be 1, which is similar to when we have barium and calcium basically sharing the same site, so that the sum of the coefficients needs to be 1. Similar here for titanium and zirconium. So this is also the case when I use a comma below, that two different elements are sharing one site in the structure. Okay, KNN is a quite well-known lead-free alternative. It can be doped both for soft and hard properties. In terms of temperature, well, it's a fairly high temperature material. You know, some variants can be used at higher temperatures than PCT. There are also quite a few that are intended for a bit lower temperatures, like around 200 degrees, but that depends on the composition. But quite versatile lead-free alternative. As you see, you have pluses all over here. Then a related material where it's lithium sodium niobate, mostly with in this case with a high content of lithium. In this case, for example, for single crystals, you can get very hard properties, and this is also useful for high temperatures, but generally not soft characteristics. Then another very promising material, sodium bismuth titanate with a barium titanate. So it doesn't really make sense to look at it in the pure form that is normally called NBT or BNT. So I actually put it together with barium because normally there's a certain percentage of a barium titanate together with the NBT in order to get useful properties. So you can get soft characteristics to a certain extent, but it's especially relevant for hard characteristics. So I can say in the cases where I put 2 pluses, it actually means that there are certain very nice features of some of these hard lead-free alternatives that you can actually drive them very, very hard. You can get to a very high vibration velocity, and still you will keep the let's say the hard properties, the high mechanical quality factor and so on. So some of these are actually very promising for certain high power applications, like the case here for NBT-BT. It will not really be a high temperature material because in the NBT-BT you have a depoling temperature, as I will mention a bit later, which is quite a bit lower than the Curie point of PCT. Another interesting material is bismuth ferrite, also generally used in a solid solution with a barium titanate, and I write it like this. Next material is not so well known. It's developed in Japan. It's a group of material called the tungsten bronze structures, and one example is mentioned here. And this is interesting for again getting very hard properties and a material that can be driven at very high vibration velocity. And some of these tungsten bronze materials can also be used for quite high temperature. Next, a real high temperature material, the group that is sometimes called BLSF, the bismuth-based layered ferroelectrics. We also call them Aurelius phases, and some well-known examples are this bismuth titanate and strontium bismuth titanate here. So they are actually quite hard, and they are characterized by Curie points typically above 500 degrees, and in some cases above 700 or 800 degrees. So real high temperature materials. Generally, the coefficients are a lot lower than for PCT, maybe D33 around 20 picocoulomb per Newton, where it could be 20 or 40 times as high for a normal PCT. Then, of course, there are quite a lot of combinations of these materials systems. You could make a combination of the KNN and LNN to get better properties. You can also, for example, combine KNN with NBT or with even this BCT set that I mentioned up here, and then you can get quite a range of specialized properties. In the end, a little later, I'll also mention some very new electrostrictive materials that are quite different from the PCT and from all of these materials that I mentioned above. So I'll show you that in a minute. Okay, so I should also mention that very often it's necessary to use very special techniques to compensate for difficult processing. There's mechanically activated synthesis. There's templated grain growth in order to get a sort of oriented textured structure to maybe make the material resemble a little single crystals and getting better properties like that, and also special sintering techniques. But the important point for now is that you should not expect any drop-in replacement. You could not take any of these materials and just replace a piece of tea with that and then expect everything to work as you hoped. And I think Baltra will actually show you an example of that in the end of this webinar. Okay, so I think I'll make these examples short. I'll just mention for KNN that you generally get relatively high D3 coefficients and in some cases quite a nice operating temperature range. But there are certain problems with KNN that makes them difficult to make, and this is maybe one of the reasons that they are not really that dominant on the market as you could expect, since they have been under development for quite a long time. And one specific issue is also that it contains, of course, niobium, which is a more expensive material than the precursors for PCT, and there's also some environmental concerns with the niobium. Also, very briefly about the NBT-VT materials, you see here one example with a 4% barium titanate, where you see this concept of this, it's a relaxer-based material, and it actually shows some relaxer behavior as seen here, and there's also quite low depoling temperature, as you see. But still a very promising material and not as difficult to make as KNN. Then just a few words about these electrostrictors. There was actually a webinar mentioning quite a few details about that in the spring series by Vincenzo Esposito. But in short, potentially you can obtain a very high D3, extremely high, up to 200,000 picometer per volt, but generally at very low frequencies. So we are luckily in a project where one of the aims is actually to take these very nice properties of these electrostrictive materials and take them to higher frequencies than just a few tens or hundreds of hertz. So we hope that we can give you news about that within the next few years. Okay, so now I've come to the conclusion, basically the status on the RoHS-directive is that we hope that the new expiry date will be July 2026, and we will also apply for the further extension in order to be able to develop materials sufficiently well. And there's been a lot of research on lead-free alternatives, but generally we still need more time, and we on the other hand, we have quite a few good promising candidates that we hope to offer for many applications in the future. But it will generally be necessary to make a design change for a specific application where if you are used to using PCT. Okay, this is the end of my part. I think I'll hurry up and give the microphone to Baltramiejus Andrijaitis. So please, Baltra.
Thank you. Do you see my screen?
Yes.
Can you hear me?
Yes.
So once again, good day, everyone. First of all, thank you for joining our webinar. And thank you, Erling, for such an interesting presentation. Now we will dive to design, testing, and comparative analysis of lead-free KNN, NTK, and PCT piezoceramics in time of flight flowmeter application. Before we go into details of our study, let's take a moment and overview what we will be covering throughout this presentation. And here is what we have in store. We'll start with short introduction. We will delve into the objectives and background. We'll outline the methodology and approach. Next, we will discuss direct replacement of lead-containing ceramics with lead-free. After that, we will explore strategies how to improve lead-free transducer by providing finite element analysis and experimental results. And finally, we will wrap up everything with conclusions and possible future work. Our study is driven by several key factors, which each with the goal of evaluating suitability of lead-free KNN type piezoceramics compared to traditional lead-based PZT materials. So, two approaches were taken to address this research: a direct replacement of active elements. Here we aim to explore the potential for direct replacement of lead-containing ceramics with lead-free and assessing their effectiveness in this role. In addition to direct replacement, we will investigate design improvements that could enhance the performance of lead-free flowmeters. In the end, we will establish finite element analysis basis for modeling the flowmeter, and we'll compare all the results together. So before we delve deeper into our study, it is important to understand the driving force behind our research. I will be fast here because my colleague Erling already introduced RoHS-directive. So I'll just mention that this directive is planning to forbid lead-containing electronics. This ignited the research of alternatives for lead-based ceramics, such as lead-free. So this search is focused to look for answer: is lead-free ceramics, if lead-free ceramics could be substitute for lead-based PZT. Moving to our methodology and approach, it is important to understand how we conducted our study to achieve objectives provided before. So these are the main steps. We initialize our study by comparing essential material properties of lead-free ceramics and PZT ceramics. We will provide some assembled pieces of flowmeter transducer. We will provide finite element analysis and calculation of the model. We will provide some data of our assemblies measured, and finally we evaluate and compare the data together. Now let's discuss, now that we discussed methodology and approach, let's dive straight into the heart of our findings. We conducted a comprehensive comparison between PZT and PZT NC51 material, which is produced by CTS, and KNN NTK type lead-free material LFP0401, which is produced by company Nitera. And let's start our analysis of table with the electric constant, because this property describes the capacitance of piezo, which is also important parameter for the transducer. The higher the electrical constant, the higher capacitance should be in theory. However, in this case, not in this case, but in generally, capacitance is inversely dependent on frequency constant, which we can see here. and the difference is quite high. So it means that overall capacitance of lead-free material will be unfortunately lower compared to NC51. Also, all other parameters, including density, are lower. However, lower density could be advantageous in this case because in fluid flow meter modeling, because density is directly proportional to acoustic impedance, and in fluid flow meter modeling, the lower acoustic impedance transfers energy more efficiently in this our application. Now that we are familiar with properties of lead-free LFP0401 material and compared the lead-based and compared it to lead-based material, let's take exploration one step further. So there are a comparison of previously introduced material in the shape of OD disc 7 millimeters. OD is outer diameter 7 millimeters disc, and finite element model is presented. Simulations were performed with on-scale software. On the left, we see quite good matching. On the left, we see quite good matching of the curves of lead-free samples. There, the material matrix was tuned accordingly to measure data, cooperating with on-scale team. And on the right here, we see lead-based material, and you can see curves are a bit mismatching, and because this wasn't tuned. The same comparison was done in higher frequencies. Here on both graphs, we can notice a mismatch of materials damping and mismatch of resonance frequencies, which indicates that our matrices of material could be tuned more. However, resonance frequency do not differ more than 4% in here, in here, here, and here. And we assume that the finite element models are valid for further development. Before going further to the finite element analysis of transducers and designing, let's shift our focus towards the principle of time-of-flight flow meter. So basically, this flow meter measures the volumetric flow of the fluid of the fluid in pipes. The pair or more transducers are required to perform the measurement. Here, acoustical waves are transmitted by means of flow meters in both directions of the flow, together and against it, that you can see in the figure 5. And time of flight of the acoustical wave from one transducer to another is affected by the speed of fluid. And as we can see from the formula, the difference between these two times is directly proportional to the flow velocity. Now let's dive into our investigated case and the design of flow meter transducer. At first glance, the flow meter design looks quite simple. We have casing material, which is purple, a piezoceramics, which is green, and backing layer, which is blue, and a layer of glue. However, there are some challenges in designing and assembling the flow meter. First of all, choosing the correct material and thickness for matching layer. I'm talking about a casing material here. Also, we must choose robust glue and achieve as thin layer of glue as possible while assembling. Also, to ensure parallelism of casing material outer and inner surfaces with respect of the ceramics flatness. And here on the right, you can see the section view of assembled lead-free time-of-flight flowmeter, which we used in our assembly, and it is also involved in our results. Parallel to assembles, axial symmetrical model was created using the same on-scale software. The first one, you see it on the left, is for transducer impedance response definition, and the second, you can see it on the right slide, is to record pulse echo response to evaluate overall performance and compare with the real samples. For the second model here, mesh was chosen not to show because distances there are quite high. It's approximately 16 millimeters, and the image would be black, basically, with the mesh. Also, it is necessary to mention that both finite element analysis were run without a backing layer. Instead of backing layer, we were using void to reduce the complexity of the model and due to the lack of accurate properties of epoxies. What is important to perform an accurate pulse echo, we will discuss in further slides. So here, as well, we have a comparison of lead-free and lead-based transducers. Again, on curves, we can see some differences. These differences could come from various sides, from material metrics inaccuracies, quality of assembles, and differences in geometry of ceramics, because in real case, we use ceramics with wraparound, and in the model, we performed the edge-to-edge electrode. However, again, differences are not significant. It's up to 5%. So model was considered as good to continue. Sorry. How do I run it now? Sorry, technical difficulties. Oh. No. There is a marker. Oh my God. Ah, it's here. Sorry. So. Finally. This is the video pulse echo simulation. We can see high frequency 20 pulses that were excited in the ceramics traveling in the water, hitting the mirror, and traveling back where the echo signal is read. So here talking about what is important to perform a good pulse echo finite analysis. It is important to measure that high acoustical impedance material should be used for the mirror. In this case, it was stainless steel. And another point, distance between the sample and the mirror should be set exactly as in the real case. Otherwise, signal would not represent the real case in general. Okay, here, let's delve into the pulse echo results. They are a bit reversed here. We don't compare real cases with simulations anymore. Here, we compare lead-free and lead-based samples with each other on the right side, and simulation between the lead-free and lead-based material on the left side. So Finite element analysis showed around 27% difference between materials in performance, and measurements of ensemble reached even 50% approximately difference while comparing them without backing layer. However, lead-free samples with backing layer showed only 36% lower performance than lead containing, and this value was considered as the final one to compare them. Model in general is quite matching. The difference between simulated and assembled transducers could come. The differences between simulated and assembled transducers could come from previously mentioned reasons. As now we are familiar with the performance of lead-free assemblies, let's dive into possibilities how we can improve them. There were 3 possible ways taken into consideration. However, all of them, it seems, have some drawbacks. Changing the backing layer from epoxies to air backing could significantly increase the performance. However, it reduces environmental resistance and increases ring down. Reducing thickness of the matching layer by half of the wavelength could help slightly, but overall strength would be reduced. And finally, increasing active layer area, which would increase the size. Also, the possibility is to increase active layer area. However, it would increase the size of transducer, the whole assembly, and also the pricing. So for further investigation, we chose to increase the active layer area from used outer diameter 7 to outer diameter 9. And further, the same process of assemblies, measurements, finite element analysis was performed to get investigated changes. More graphs. On lead-free graphs, we can notice lower overall impedance values. This was caused by higher thickness to diameter ratio, and besides that, graphs look quite similar to OD7. And I will move further. Here, pulse echo response showed more similar results compared to simulations and assembled transducers. Difference in performance between materials is jumping around 35 in real case scenario and in simulation. So we get more constant values, which also was influenced by higher thickness to diameter ratio, I would say. Moving to the results, changing OD from outer diameter from 7 millimeters to 9, it seems had a significant increase. It increased by, the performance increased by 2.7 times, which means with a small change of diameter, we can enhance performance significantly. This shows that lead-free ceramics could be replaced by, lead-free ceramics could replace lead-based ceramics with a slight change in design. And the difference also, it is important to mention that differences between assembled flowmeter transducers and simulations at same parameters and conditions showed quite constant differences, what validates finite element model for further research. To wrap up, KNN NTK LFP0401 ceramics showed overall lower performance compared to our lead-based NC51 material with a pulse echo response 30%, 32% when simply replacing an active element. However, increasing active area by 29% increased effectiveness significantly by 2.7 times, which leads us to the final conclusion that lead-based materials could be substituted by lead-free materials, however, with implemented design modifications and compromise in robustness, dimensions, and other transducer properties. For the future research, few approaches could and will be taken. It's improving simulations by adjusting material matrix to match more on the thickness modes of the samples. Also, it will be considered to take into account other lead-free materials, qualify lead-free transducer, and increase the quality of assembly process, and of course the quantities of samples. That's it from me. Thank you.
Thank you very much, Baltra. So now the talk is open for questions. Actually, both Baltra's and my talk. So maybe while you are thinking, I'll just ask. So you were saying that actually the results were quite good for the lead-free material, and it can reach and even exceed. Well, as far as I saw, it didn't actually exceed, but what would it take if you needed to get even higher properties than PCT? From your example, where would you like to optimize in order to get even higher than PCT? I think you, Baltra, you are muted.
Oh, sorry.
Yeah.
Yes. So to answer this question, to exceed, it depends on the application, of course, but as I mentioned, there is no way to exceed PZT performance by 1-to-1. We will have some losses in the parameters or properties of transducers, flowmeters anyway, but I think, as I mentioned before, changing of dimensions of sample is quite a nice way to at least reach the same output as PZT material does.
Yeah. Thank you very much. And you were also asking for maybe better input data for your modeling. So I think this is also something that at least we'll be working on here in our company to improve the data that are used for modeling, so you get a better agreement between the model and the measurements. Good. So I'm now looking at the list of questions. So let me see if there's more about your talk. Yeah. Okay. So I think that there are maybe some for my talk. So I'll move to that now. So the first one is what is the price difference between PZT and KNN offered by Ferroperm? So that actually leads me to actually mentioning, I didn't really mention it clearly, that we do make KNN at Ferroperm. We have two types which are still types that are let's say on the prototype basis, and I would invite you to ask if you would like to have samples. And we also have two NBT based materials. Anyway, about the price difference, well, I cannot really give any percentage. I can confirm that KNN is quite a bit more expensive than PCT, but I would actually need to refer you to our sales department. But still, please try to get your own experience with the new materials. Next question I have on the list: Can you provide details on the major challenges for synthesis of KNN for commercial applications? Well, I mentioned some details that, it is, during the process, the KNN is actually quite humidity sensitive, or the precursors are quite humidity sensitive. So you need to take extra precautions, which actually makes the process more expensive. And also, it's really a challenge for the manufacturer to get a good reproducibility. But of course, this is something that we are working on improving. So that's the most important points I would mention there. Next question: how is the water humidity affecting lead-free ceramics in storage or in the instrument with epoxy seals? Well, actually, once the material has been successfully made, it's actually not sensitive to humidity in the same way. And I can actually refer to a paper that has been written by a PhD student of ours. I advise you to search on that. The main author is Gianni Ferrero, but there's a paper on the humidity influence of manufactured ceramics. Next question. I think we are running over time. I hope some of you have time to stay a little longer. So yeah, the price difference. Have you tried, next question, have you tried KNN NBZ for a transducer? No, we don't have any let's say, any materials that we can offer now, which are a combination of KNN and NBZ. But I know that there's some interesting samples or interesting compositions have been made in the lab, but we haven't tried this in our department yet. Next question: are there any standard values, for example, of D3 and Curie point, that lead-free ceramics should attain so that they'll be able to replace PZT? Well, I think the short answer is no, that there are no standard values. I think you actually need to look at applications from case to case. There's been a lot of attention to D3, and one of our points is that D3 is not enough. It's just to try to match. You should actually look at maybe D3 as one sensitivity parameter, together with things like temperature, behavior, losses, both dielectric and mechanical and piezoelectric and so on. So you should look at all things. So I cannot really give any specific values, but my general advice is to really try to look at a specific application, like Baltra also did, and then see what are the issues. For example, if you have too low permittivity, maybe you will get a difficulty in the electrical impedance matching. So then you either need to change the design or try to increase the permittivity. So this is not really a comprehensive answer. It's just indicating some things you need to work on. Next question: what are your thoughts about lead piezoelectric nanomaterials with high piezo constants? Well, I think probably you are thinking, Nilesh, about lead-free piezoelectric nanomaterials. Well, we don't have a lot of experience with such materials. We are really mostly on the bulk side of piezoceramics, but I think that there are some quite interesting materials there. But for most of our applications, you actually need some volume in order to transform some energy. Of course, if it is a sensor, for example, where you are able to amplify an electrical signal, then a nanomaterial, for example, in a very thin layer, could actually be quite useful. But personally, I don't have a lot of faith in for example, nanomaterials for energy harvesting and so on, because I think the problem will always be to scale it up to get a sufficient amount of energy converted. Yeah. Okay, I think I'm almost through my list now. Yes. Final question before we close. Can 1 micrometer grain size barium titanate replace PCT in low temperature applications? Well, I think in principle it could for some applications. I would not rule out barium titanate and related materials if it's really for low temperature. And then of course you need to look at all the properties the other properties that I was hinting at, not only D3 but also coupling coefficients and permittivity and mechanical properties and so on. But I could certainly imagine applications where small grain sized barium titanate would be useful. Okay, so thanks to all of you for staying with us even 6 minutes over time. So I would like to say thank you to Baltra for a very interesting talk. And
thank you for listening, everyone.
Yeah, thank you. And also thanks for everybody. Thanks to everybody who joined this webinar. And I hope to see some of you for the next webinar, which will be in, as far as I remember, in 2 weeks. But I'm sure you will be informed by the usual channels. But let me just confirm before I close that the next webinar is actually in 3 weeks. It's on Wednesday, November the 15th, and it will be by Dr. Marcus Kane, and it will be really going into details with measuring D33. So thank you for now, and hopefully see you at one of the future webinars. Bye.
Bye.